So here I just want to cover some of the material from chapter 28, which was on magnetic fields. The idea here is at the end of the magnet that points towards the geographic north, we call it the North Pole. Now this is really just to be able to distinguish like which one's the north and which one's the south pole of the magnet. But what we see is that if we have two magnets like this, we know that they have a north side and a south side. So this is the north pole of the magnet and this is the south pole of the magnet. And we also know that there's no such thing as a monopole. You can't have just a north magnet. You have to have a north side and a south side to your magnet. Now you bring two magnets close to one another and you say that because opposites attract, we have the south side of the magnet being attracted to the north side of the magnet like this. I'm going to stop saying the word side because they're really called North Pole, South Pole. Now, if we were to imagine the Earth as having a magnet inside of it, the north side of the compass, well, we know that pretty well points north, as in geographic north. And that's how we actually use a compass to figure out where we're going. It's through this. And now remember that this is literally just a magnet. It has a north side and a south side. But then when you think of it, well, the north is attracted to the south. So that means the south side of the Earth's magnet has to be up here. And the north side of the Earth's magnet has to be down here for this process to actually work like this. So we call this the magnetic south and this the magnetic north. Now you see that there's a difference in this angle between the geographic north and the magnetic south. That just has to do with the fact that the Earth's magnet does not perfectly align with the Arctic and the Antarctic. It's actually shifted a little bit here. Now we call the magnetic field B, and it's created by moving charges. We'll see this in next week. Now the magnetic force exerts, so the magnetic field exerts a force on magnetic poles. The force exerted on a north pole is in the direction of B. So if we place a compass here in a magnetic field, well, the north pole of the magnet feels a force in the direction of B, and the south pole of the magnet feels a force in the direction opposite, so down here. So what's actually going to happen is that we're going to have this rotation such that the north is here and the south is here, so that they actually align with the magnetic field. And this, again, is how this magnet works to be able to tell you where is the kind of close to geographic north. Now the units of the magnetic field are in Tesla, and Tesla is 1 Newton per amp meters. Now we can also draw out our magnetic field, and we see that they start at the North Pole and they loop back down to the South Pole like this. So start at the north and they loop back down like so. A way that you can think of this is if I were to have a compass positioned somewhere along here, I would see that the magnetic field B, it points in the direction that the north pole of my magnet would be pointing. So if I were to put here, for instance, a compass, well, my north is here and my south is here. So it's just like, how is the compass aligning itself due to the fact that I have a north pole here and a south pole here. Something you're going to see all the time is something called the cross product. And it's basically just a method to multiply two vectors. Because remember, we already know the dot product, A dot B, is equal to AB cos theta, where theta is the angle between A and B. And see here that this is a scalar quantity. The idea here with A cross B is that we have A, B, sine of theta. So this is the magnitude, because the idea is that A cross B is actually a vector quantity. And we're going to use the right-hand rule to figure out where this new vector is pointing. And I'll explain that in 1 second. But first, how do we mathematically deal with a cross product? Well, it's not too difficult once you understand the pattern a little bit. You're going to take A cross B, and you're going to draw this little thing out here. This is the determinant method. So you're going to draw two bars like this. Then you're going to say I hat, J hat, K hat like this. Now you're going to take A and say, well, what is A? What I mean by that is, what is the A component in the X direction? What is the A component in the Y direction? And what is the A component in the Z direction? And then you're just going to place it here. So this is AX, AY, and AZ. You're going to do the same thing for B. So what is the component of B in the X direction, component of B in the Y, component of B in the Z? So now you're going to take the determinant, and if you don't know how to do that, first thing you're going to do is cross out I, like so. So we want to start with I, so you're going to do, I'll draw it out in red, cross out this, and cross out this. Now you're going to say AY times BZ minus AZ times BY. So do this times this, minus this times this. And you place it like so, and you say that is A cross B in the I hat direction. The way you remember that it's in the I hat direction is because you had to cross out I to get there. So again, start off with I, cross its column and row out like this, AY times BZ minus BY times AZ, like so. Now, we're going to do J. Same thing, cross out J's row and column, like so. And then you do top left times bottom right, so AX times BZ minus AZ times BX, and you place it like this in yellow, and that is the J hat direction. Now you're going to do the exact same thing again for K. Cross out K's row and column, AX times BY, that's here, minus AY times BX, and you place it here, and that's your new vector in the K direction. The only weird thing is that you're going to have a negative sign here before the J. So as long as you remember cross out row and column, top left times bottom right, minus the other two multiplied by each other, and then in that direction, then you're just going to have to add a little negative sign here. The more you do this type of problem, the easier it's going to get. Now, if you remember, I told you that we're going to have to use the right-hand rule to figure out where is our new vector. So here we have A cross B, and the magnitude, we can just say is AB sine theta, right? So we can do that, or we can just figure out where exactly is it in the I, J, and K, because this just gives you magnitude. So if we want to know where is it pointing, you're going to have to do the following. So you place your index finger in the direction of the first one. So here, the first one is A. So your index finger is going in the direction of A. Now I want you to place your middle finger in the direction of B. So this is index. And it might be weird because your fingers don't really want to go exactly like that, but that's fine. This is the middle finger, as long as you get it pretty close. So index is pointing in that direction. Take your middle finger and point in the direction of the second one, and then stick your thumb up. The direction of your thumb is A cross B. So thumb, that's A cross B. We're going to do a couple of examples later on in the problems where, because this is so common using a cross product, you take your index in this direction, middle in this direction, and then wherever your thumb is pointing is in your new direction of your vector. So that is about it for cross products. There's one more thing. When it comes to notation, we're going to be using these little things. So whenever we have x, like an x, that is saying that the vector is in the plane, and a dot is saying that it's coming out of the plane. So that's just going to make our life a little bit easier. And where this is the x direction, this is the y direction, and we're going to say that here, if I'm going this way, well, it means that I'm going this way into the plane. So instead of trying to like draw some weird three-dimensional stuff that's decently hard to do, we're going to use this notation. The way you remember it is you have an arrow, right? So you have the feathers of the arrow here, and then you have the point of the arrow here. You think of this being what you see. So if I see the X, which is the feathers of the arrow, that means my arrow is going this way. But if I see this coming right at me, that means I'm seeing the point of the arrow shooting at me, which means that that is coming out of the plane towards me. So now we can actually calculate F, where F is the magnetic force, right? So this is F, and you're just told that this is the equation that we have. Is Q times V, where V is the velocity of your charged particle, cross B, which is the magnetic field. Don't worry about how we got that. For now, just trust this is the equation to find the magnetic force on a moving charge in a uniform magnetic field. So for instance, let's say we have this charge as a positive charge and it's moving in this direction. So this is V and this is B. Now we know that the magnitude of F is going to be equal to Q and then VB sine theta. So that's the magnitude, because that's just what the cross product is. Now if I have this here, well, the angle between them is 0. And we know that sine of 0, well, that's going to be equal to 0. So that means there is no force. So whenever we have our particle moving in the same direction as our magnetic field, it experiences no force. On the opposite side, here we see that the velocity is moving up, B is moving here. Well, that means that they are at 90 degrees to one another. And sine of theta, or sine of alpha, whatever you want, the angle between them, if that is 90 degrees, sine of 90 degrees is equal to 1. So we have a maximum value here. So whenever B is at 90 degrees or perpendicular to V, we're going to have a maximum force experienced on our little charge here moving in that direction. Now we want to know where is that force pointing. So we're going to have to use our right hand rule, or we're going to take V, use our index finger to point in that direction, B to point with our middle finger in the direction of B, and then our thumb points in the direction of F. So pointer finger, your index finger goes in the direction of V, put your middle finger in the direction of B, and then wherever your thumb's pointing, that's your force. So we see here that my thumb, if you do it, your thumb's pointing down, and down looks like this, where again, this is like seeing the back side of an arrow, where the arrow is pointing into the page. So we see that our force is going into the page. If I were to draw the situation like so, where here, B is pointing into the page like this, and then I were to look at my particle, and I'm saying, well, it's starting off with a velocity going down like this. Now, where's the force? Same thing. Pointer finger goes in the direction of V. Middle finger points in the direction of B. And then where is your thumb pointing? And you see here that your thumb is going to be pointing to the right. So that's what we have here. So if it's going to the right, that means it's going to experience this force in this direction. And then what happens if it experiences a force? Well, it starts to move more in that direction. So what we see is that it moves in this direction. If we keep doing this, so if we have this as our new situation and we say, where is our force? We do it again and we have our force pointing this direction, which means that our particle is going to start moving closer to that direction. And if we keep doing that, what we see is that our particle starts moving in a circle. So a particle starts here and then it just does a loop like this. So what we can see is that if V is perpendicular to B, which is what we have here, so this is our B and this is V, where they're always perpendicular to one another, right? Because this is going in the plane and this is just going, it's in this XY plane like this. That means F is equal to QVB, because sine theta is equal to 1. And then what we have is a relationship for when we have centripetal acceleration. So we've seen this in Phys 204, where if we have a particle that's just moving in a circle, the centripetal force that it experiences is mv squared divided by r. So that means that if we have this situation where our particle is going in a circular motion, it's experiencing centripetal acceleration, which means that we say that this is also equal to qvb. So then we can figure out what is the radius that our particle moves within. So if I have my particle here, it starts moving in this circle, and that circle has a radius r. What the radius is, we just solve this equation here, and we see that r is equal to mv divided by q times b, like this. We can also talk about a couple of other things. For instance, we can say that omega is equal to v divided by r, and then if we know the relationship here, we solve for qb divided by m. We can also talk about the period, where this is the definition period. All of these things you have hopefully seen before in Phys 204, but pretty well the only equation that you should be really using is this, where if you know that your particle is going in a circle, the radius is r is equal to mv divided by qb. Now, when we have a charge moving in both an electric field and a magnetic field, it experiences both forces from the electric field and the magnetic field, which we call the Lorentz force. And it's written out like this, where the Lorentz force is equal to Q times E. We've seen that before. This is the electric force, plus QV cross B, our magnetic force. In the next video, I'll talk a bit about torque and magnetic force on a current carrying wire.